We can wait until the 35, like 5 minutes courtesy. Sure. Here's the second. You have it. He gave you the first one. It's okay because here is the rest of the. Okay, yeah, but it's just to maybe put them together so that we don't lose one of them. I think it's there. Yes, I just. Check. Okay, so good afternoon, everyone. I think we can start after waiting a few minutes of courtesy for everyone to join. So I suppose that everyone can hear us and everyone can see, and the presentation sharing is okay. If not, you can leave a comment in the chat. So welcome to this to another webinar of the INGENIous battery cluster. My name is Evelina Castellana. I work from Lomartov, and I'm here representing today VersaPrint project. Since we are a partner of it, I'm leading the clustering activities within this project. So today we're here for the webinar titled "How do we ensure safety in the next generation battery design?" We'll be together until 3 this afternoon. And yes, we're here today with several projects of the clustering. Before that, I will just give a few rules, as you all know. So keep your audio and video off for the participants. They are disabled. They're able only for the presenters. But we will have a question and answer sessions, and you can write your questions in the team chat. So during this session, we will all the speakers will try to give an answer the best way possible. The session is being recorded, as you can see from the red dot on the left on Teams, and we will also share the recording on this side this time on the VersaPrint website and the social media. Since this webinar this time is hosted by VersaPrint project. Here you can see the link on the different networks we're working on. So first of all, the INGENIous cluster that is reuniting all the 5 projects of this cluster. So BATS, Extended, NextBot, Tempest, and VersaPrint. So here is the agenda. As you know, so we'll have a first introduction from Lisa Lu Gracias from CEA, the coordinator of the VersaPrint project, and then we'll jump into this first session, the strategy to tackle safety technological bricks within projects. So we have 4 of our projects, or BATS, Extended, NextBot, and VersaPrint. And then we'll have the session 2, we will have a very interesting discussions with all the speaker, and then finally the closing and the wrap-up. So I will hand the word to Lisa Lu.
So thank you very much, and again welcome in this to all of you in this webinar. So as Evelina introduced me, I coordinate the project VersaPrint, and today we organized this webinar, but we represent the cluster EU INGENIous, and this is a cluster that brings these five projects together because we work on the same objectives, targeting to design and to produce new next generation battery systems. And we do so at system level, which means we do not work on the chemistry level, but at system level. And this is what makes us work together as a cluster. So as Vina said, today the focus will be about safety. We almost all of these projects reach the final year and the final month of our project. So this was the opportunity for us to discuss and show you how we treat safety in this next generation battery systems. So I think we can start with the first session.
So, yes, I will hand the word to the first speaker, Manex Larrañaga from BATS project.
Hi everyone, can you hear me?
Yes.
Yeah, okay. It's a pleasure to be here. So I'm Manex Larrañaga from Citadel Energy Storage, main coordinator entity from BATS European project. And today I'm here to talk about the strategies we integrate in the design of the main battery system to tackle safety aspects. And the main path we have been following during all the project is... Sorry, is someone asking or... No.
No.
Okay.
Okay, you can go on.
I will follow up. Yeah. Okay, so
switch the screens.
No, it's for us. It's okay. For them, it's okay. It's okay. For us.
Oh, so if you yes.
Yeah, sorry, Manex, you can go on.
No problem.
Don't see the. Oh, I have one slide.
We usually have the similar problems. So the main path we have been following during all the project is the one based on safe by design concept. And this is something that has been integrated in all the different aspects of BATS battery system solution. So as you can see here, I mean, I'm highlighting different aspects because the safety aspects are not only the ones that can be integrated in the physical solution of the battery system, are to the ones based on control strategies, monitoring, standard identification, and all this stuff. But to summarize a little bit the main aspects that have been evaluated in this safe by design concept, we can start evaluating the ones based on thermal solutions. And for example, considering the thermal safety aspects of the battery system, I think that one of the main components that I have to highlight is the flex cooler. That is an innovative thermal management strategy that, apart from defining a higher thermal performance and characteristics than the conventional cooling strategies based on cold plates, these components that it's integrated in BATS solution additionally integrate a safety barrier between the battery cells that can face a thermal runaway propagation. So it's a safety component that it's integrated with the main idea to be the safety barrier. So that's really interesting. And another innovative component, and it's, for example, the cell type we have integrated in BATS solution, but it's a high performance 46XS cylindrical battery cell. And the main one of the interesting aspects of this cell is that enables the separation of the venting area from the life path. And this is something really interesting that improves the safety aspect of the main solution. And to finish with these thermal solutions, and we have more examples as all the preliminary experimental and numerical studies that we have developed to evaluate the thermal runaway phenomenon and the venting gases to integrate from the beginning in the design of the adequate safety barriers and our components to improve the safety performance of the solution. And more or less, those are some of the thermal solutions that we propose in this project from the beginning, and how we tackle the safety issues in the design, considering the thermal solutions. If we consider the electrical and BMS solution, that is the next slide. Yeah, this one, and here we can talk about ultrasonic-based structural health monitoring that it's evaluating people from IT in the BATS project. That is really interesting, and we can talk about wireless solutions to enable integrated cloud communication. And I think that that's really interesting because this solution provides a constant battery system monitorization, allowing for real-time information to evaluate the system current conditioning and to predict, for example, future performance. And this is, I mean, apart from another aspects, some of the main topics. And if we jump to the next slide, we can talk a little bit about the mechanical. And here, finally, we turn, as mentioned, to the mechanical solutions that have been integrated in line with this safe by design concept. I think that I will highlight the work that has been done from the outset to incorporate the standards and specifications defined for each application into the design of the battery system from the beginning. That's really important, and it was quite heavy. Because it should be noted that INGENIouS project has developed a modular solution designed to meet the requirements of marine and off-road application and a second life use case. So it's quite distinct solutions. And this is why it is quite complex to incorporate all the safety strategies and design specification requirements for different applications in a single design. So it was quite heavy to start from the beginning, evaluating all these standards and specification and integrate these aspects directly in the design, following this safe by design concept. And those are a few highlights of the strategies used in BAT's project to tackle the safety aspect. So if we jump to the last slide. Yeah, so in this final slide, I mean, I will give you a brief overview of what I will be exploring in more detail in the second session. I will focus on, as you see, the thermal solutions we propose for BATs and how we evaluate and select them, considering the thermal runaway propagation scenarios and venting gas distribution. I will show you a little bit how our selection process was based on a combination of experimental data and numerical models. And I will be talking about some other thermal solutions that we are proposing in BATs and how we close the loop more or less and evaluating from the main requirements and the main solution and the main validation, experimental validation, and how can we close the loop in this project. And I think that's all from my side for this first session. Thank you very much.
So thank you very much. Yes, now the microphone is on. Thank you very much, Manix. I will share again the screen. I don't know if we have questions up to now, or no, we jump directly to the next presentation. Just 1 second. I will keep our microphone on.
No, yes.
Oh, yes.
Yes.
So I just
But
have to keep it in the Sorry for this logistical problems. It's just that since we are in person here, we just have to arrange some small details. But now it's good.
No problem.
Are you connected to?
Thank you.
No.
So I'll hand the word to the next speaker for extended projects.
Okay, thanks. Can you all hear me?
Yes.
Yes. Okay. So my name is Borja. I'm coming from Mondragon University in Spain. And first of all, I would like to, of course, thank the organizers for inviting me personally and of course the extended project to share with you some of the findings and strategies we have been using for the project. Go to the next slide, please. So what I'm trying to do here is just for you to accompany me through the thought process we've been through when we have been doing all the research through the project. So the main, at least the main question that jumps to you whenever you want to do this safety assessment is that how do we evaluate this the safety performance of the battery? And in this particular case, we're concerned about if you see the sketches that I'm showing, we're not going to deal with the module itself, but we're going to deal with the cell. Okay, as a let's say the representative minimum let's say element that we want to assess. And in this scenario, we can think of many things that can happen to this cell. I have shown you one of the many things that can happen, which is a crash between two cars that are supposedly electric vehicles, but can be any number of things. Okay, and one thinks of things that can happen, right? So we can have crash or penetration scenarios. We can have quick overcharges and discharges. We can have external short circuit due to debris or erosion, things like that. And of course, we're going to be exposed to elevated temperatures, either by something that catches fire or thermal runaway coming from other cells, right? So how do we do this? So ideally, what we would like to do is to take our cell and start doing some experiments, right? Some experiments that in most of them are standardized. We'll see later on that this is something that we run into issues with, but that's for later. So we want to perform experiments, right, to evaluate all these different things. The problem is that these experiments are quite expensive. We need to essentially take our battery cells and destroy them. So most of all these experiments are destructive. Oh, sorry, we jumped to the next slide. That was intentional, or was it an accident? Okay, thank you very much. So our goal in the project was to, okay, let's do this experiment, but the goal is that if we can make this a little bit cheaper through finite element simulations that in a way guarantee that these simulations are going to perform ideally as the same as the experiments. If we do this virtually, we're going to save a lot of money. Okay, so now yes, now you can go to the next slide. Okay, but whenever you do certain finite element simulations, it comes with a lot of challenges and the results are going to be seen in the next session, by the way, but I just wanted to highlight a little bit of the obstacles that we went through when we were performing the project, right? So whenever you think on a battery cell, it's because of my background, I always think on solid mechanics, okay? Because my background is on solid mechanics, not in chemistry or other topics, okay? You need to think on a finite element code that allows you to do many things, not only the mechanical aspects, but also the thermal and the chemistry of the battery and the electromagnetic aspects. Okay, so first of all, you need to find some code that does all of it simultaneously, which is not easy. Okay. Also, as the previous speaker said, you can have issues with the venting, and this is something that we have not tackled yet, at least in this project. So there's nothing coupled with fluid mechanics. So this is something that I would like to highlight. Second, you need to determine which are the experiments that you have to do in order to characterize all the different behaviors that the cell has: mechanical, thermal, electromagnetic. Okay, and then you have to figure out which criteria are you going to use to start internal short. And next, which criteria are you going to use in order to, let's say, start the thermal runway. So these are things that are not trivial at all. One might think that these are come directly in the code, but it's not true. This is not trivial at all. So you have to figure out how to do these things. And this is related to the next point is related to what I said before about the standardization of the tests. Which tests do we need and what information is important for us from this standard test? Most of the standard tests give you information about pass or no pass. Let's say that you do a test on a battery cell and then the standard tells you, okay, if you have done A, B, and C, then your cell is okay. Otherwise, it's not. But this is not an information that is rich for us to validate our simulation. So we have to, as I show in there, you have to record the force, the displacement of whatever you're dealing with, the temperature histories, the voltage, the current intensity. You have to do all these things in order to be able to validate later on your finite element simulations. And the last point is probably the most important because this is for the future and archiving what we have done, which is to produce a series of guidelines and recommendations once everything is that we understand what's going on and how it works. We have to produce a series of guidelines and recommendations for this battery cell safety evaluation. Of course, it's a virtual safety evaluation. So yeah, and that's pretty much it. All the results are going to come in the second session. So if you guys have any question, I would be glad to answer any of them.
Thank you very much, Borja, for your presentation. So we can move on now to the next speaker. Second, the next one will be NextBit project. So with NextBit project, we have Arnaud Mestre from AP Plus Laboratories. Let me just share just here, and you can go on.
Yeah, thank you very much. So hi, good morning, everyone. My name is Arnaud, and I work at Applus as a thermal test engineer. And in this session, I will address the main challenges and also the strategies related to safety in new battery model designs. Well, as we are a laboratory company, we would like to present an overview of the market and then make a brief approach on safety strategies. So in the next session, we will show you the results on safety tests that we carried out on different cell designs. So if you could, thank you. First of all, I would like to emphasize the rapid global expansion of lithium-ion batteries across also in different applications, just including mobility as electric vehicles, but not also in mobility. It's if not in stationary storage, sorry, and consumer electronics. So as you can show in the chart, they are increased exponential over these recent decades. So what does this evolution means in terms of safety? Well, as battery systems became larger, more energy dense, and also integrated into public and industrial environments, then battery systems design must ensure it is safe operational under normal conditions and must also be capable of preventing or mitigating these abuse scenarios. And these inputs will be defined by testing the new battery system designs. So in the next slide, we would like to punctualize another important point, that is the highlight on continuous evolution, continuous evolution, and research toward high energy density technologies. Well, in this slide, you can see an example comparing the operational characteristics of two widely installed chemistries, as there is an advanced NM cell, that is the blue one, and then the green one is an LFP cell. So if we focus on the relationship between energy density and safety, we can observe that increasing energy density may result in a reduction of safety margins. So while higher energy density enables the same amount of energy to be stored in a smaller model volume, well, the energy stored per cell increases. Then, of course, this pathway is necessary, but be careful because it can lead to a higher severity of failure events. So in next slide, thank you. Once we have an understanding of the current market and also the near future trends in lithium-ion battery design and installations, we can focus on several key safety topics related on thermal runaway. All of you knows that this event remains the most critical safety, concerning it's characterized by an uncontrollable temperature rise and then sustain it in a high temperature, that this volume of temperature can ignite surrounding non-battery materials. So in addition, in this thermal runaway event, more gas releases occurs and also introduces toxic and flammable hazards. Also, we have to be aware of the explosions and projectile effects caused by an overpressure of the cell in case of thermal runaways. It is important also, to note that the detection time before thermal runaway is often very limited. So maybe we could improve this detection for prevent this thermal runaway event. And finally, at the last slide, we want to address all these safety challenges. So we propose a multi-layer safety strategy applied always across the different design levels. So it means that we propose this multi-layer safety from cell to module level and from cell to module to pack level. So what we propose is battery fire safety can be structured in these four sequential protection layers. First of all, prevention, that it's focused on intrinsic safety. So it's proposed that manufacture safer chemistries and robust electrical and thermal designs. Then detection, that it relies on early warning via BMS and additional sensor monitoring parameters. Then the compartmentation, that aims to limit fire propagation by reducing heat transfer between adjacent cells or includes modules. And finally, the suppression targets to flame extinction and battery cooling once the thermal runaway occurs. And then finally, in conclusion, ensuring battery module safety requires always a well-defined design. So approach that prevention, monitoring, containment, and also mitigation from the earliest stage development will be the best key to prevent these fire incidents in batteries. So thank you all for your attention.
Sorry, just take us a few seconds before jumping to the other window to open the microphone. Thank you very much.
No problem.
For your presentation. And it's now time for the Versaprint presentation from CA. Second.
Hello everyone, I'm Gail. I'm safety test engineer here at CEA, and I will present to you the various safety-oriented building blocks that we developed in Versaprint. We developed several building blocks that are oriented to safety. The first one is a printed cooling plate directly printed on cells. So this plate is made of silicone and allows to pass water inside to cool the cells during classical operations. We also developed thin sensors, like you see on the photo. We have two sorts of sensors, one for H2 and one for temperature. The advantage of having those type of thin sensor is that you can put them almost everywhere inside the module, so you can have a good idea of the temperature inside the module. We also developed a plastic to replace the aluminum casing, so a self-reinforced plastic with phase change material and flame retardant added in it. The idea of this casing is to gain weight, but also to add a safety measure on the casing to avoid propagation between modules, for example. And we also developed an exhaust gas management system, and this is the thing I will present to you more deeply today. So to develop our exhaust gas management system, we started by taking inputs from other work package in the project, and particularly the thermal runaway characterization of our cells. So we push the gas quantity, the gas composition, the flow rate, the temperature of the gas and particles, and also the mass loss by the cell during thermal runaway. And all this led to various constraints. So we saw that the gas composition and the temperature of the gas can lead to spontaneous ignition. So we have to cool the gas to avoid flames outside our module. We have also seen that hot particles can act as an initial start to those gases. So if we can remove those particles from the mix of the thing ejected by the cells, we can limit the risk of ignition. We've also seen that the prismatic cells tend to create a secondary hole when they are abused. And we wanted to limit the overpressure at the exit of those cells to limit the probability of those secondary holes. And also we had to adapt to the nature of our module casing, because as we said, we want to make it in plastic, so it has a low resistance to temperature and also mechanical resistance. So to do so, we developed the exhaust gas management with various utility area, I would say. The first one is a collector that is placed in front of every venting unit of the cells. This objective of this collector is to gather the gases and particles ejected during thermal runaway and lead all those into the system. Then we will try to do a particle deposition, a filtering of the particle inside this mix to avoid a big particle outside that can inflame the gases. And then we want to cool the exhausted gases to avoid the spontaneous ignition. So you have here some picture of the results, but we will see it after. Thank you.
Thank you very much again. Now we can do maybe a few minutes for questions on Teams, if we have, or the speakers, before jumping to the session 2.
For the moment, we don't have any questions from the public online, but in any moment you can write on the Q&A section or in the chat.
Wonderful. And we have a question from the room, from Ilelu.
Maybe then we start the questions here, if some of you have some as well, and then maybe it can give time to people to ask more questions online. Some of you talked about the trade-off between designing components for safety, the trade-off between safety aspects and energy density, but also did you observe trade-offs with other things like cost and weight? I mean, when you design something for safety, does it automatically means that it's a trade-off between other aspects? And did you observe so, and for what? Maybe we can start with you.
I think I can start. We designed a building block that is pretty ambitious. We want to avoid flames outside the module. So we had to reduce a lot the temperature and the number of particles. So our part is pretty big and pretty heavy. So yes, it impacts the overall weight and volume of the module. But it has to be in regard of the objective that you have. We want a very safe module, so we had to put a very reliable solution. And by doing so, we increase the weight and increase the volume.
Okay, so I think, it would be interesting to ask an OEM or, especially OEMs, if they would accept, if they would consider the safety to be the priority and accept trade-off with cost and. I also thought it was, maybe we can actually, for the other projects, would you like to answer this question as well?
I mean, if you want to, I can speak. I'm Manish from BATS. I mean, what you mentioned, safety a priority. I think that nowadays safety is a priority. But for example, in BATS project, it was a quite harsh working process to balance this aspect, because as was mentioned, when you are focusing on safety, you are losing some KPIs. Considering energy density, cost, and all these aspects. So in BATS project, we were a little bit focused on how to balance all these aspects. It was quite hard, and we were in direct contact with OEMs, and it was quite shoulder by shoulder work between different partners. But it's not so easy to balance all these aspects. But I think that in BATS, we more or less reach the main objective of the project.
Okay, then I go on if there are no other questions. For the moment, I thought it was interesting what you said in your project for NextBat, and we can see that there are complementarities between the project, as the solution, the strategy for Versaprin was compartmentation to avoid propagation. Then BATS has the strategy of prevention. To detect, to have intrinsic safety features, while extended project focused on early warning, thermal runaway detection. I was wondering, for the project extended, as you specifically worked with SSB cells, which are thought to be more safer than liquid cells. How were your BMS solutions, as you designed 3 different BMS in your project? how were they impacted by the fact that the cells are solid-state cells, and did you observe any safety differences in terms at cell level and at module level between and compared to liquid cells?
Well, as Borja here from Extended. As far as I know, well, first of all, we didn't really test the solid state cells. We ran into some issues. I don't want to get into it, but we ran into some issues at the beginning of the project. The solid state battery cells were replaced by quote unquote semi-solid solid state batteries, which, as far as I know, talking to some of the partners, including yourselves, at least as far as I know, maybe I might be wrong. Don't quote on me, but the response was not very different from let's say lithium ion cell, at least in terms of safety. BMS might be, but at least in terms of safety, we didn't observe any difference. At least this semi-solid battery cells.
Okay, and could you explain us a little bit how the fact that the cells you worked with are semi-solid cells, how did this impact the design of your BMS? Of your BMS, but of your sensors, for example. I know that you, for example, that you developed sensors, pressure sensors.
We didn't work on that, so I have no information about this. I'm so sorry.
Okay.
Yeah, I'm glad.
So I was wondering because probably the solid state cells they are they have issues with swelling, so
yes,
it might be a strategy here to I think it's a strategy.
We have pressure plates, but I don't know how much pressure or what is the difference. But I know that the pressure plates are necessary. That's for sure.
Okay, thank you so much.
Wonderful. So we can close the Q&A session for the first session, and we can move on to session 2 on the verification of the strategies, tests, plan, and results. So we'll follow the same structure and speakers as before for each project. So Manex, it's your turn again for BATS project.
Okay, perfect. Back again. So, as mentioned on the first session, I will talk about some thermal safety strategies we integrate in BATS solution, and we propose, evaluate, and verify. Next slide, please. Perfect, thank you. And here we saw in some, as we saw in some other presentation, of course, and I would like to talk about how the proposed solutions were evaluated for tackling thermal runaway and venting phenomena, and how we develop all the methodology to integrate this solutions. And this includes experimental evaluation at cell level model development, validation, model scale-up, solution proposal and integration in BATS battery system design, and finally the experimental validation that will be with the demonstrator. So in this aspect, please next slide. Okay. We're going to start with the studies that have been developed to evaluate the potential impact of the thermal runaway phenomena on the solution proposed in BATS. And in this regard, numerical models have been developed and validated at module level to evaluate both performance of the flex cooler and the performance of safety components designed to cope this thermal runaway phenomena concatenation. And these studies have been focused both in numerical and experimental environments. And I must say that the results have been quite positive. And the numerical study methodology has been of great assistance to evaluate the integration of these materials. Because as you can see in the left side, and for example, we were evaluating the capacity of the flex cooler of facing the thermal runaway propagation between the battery cells, and numerically we checked that the performance of the flex cooler was able to face this phenomena, and experimentally we got some other solution that corroborates the capacity of the flex cooler to face these critical phenomena. And this is something really positive for the project, because theoretically the flex cooler is the thermal management strategy, but to add additional safety aspect is quite interesting. And in the right side, for example, you can see how we use the numerical environment to evaluate different thermal barriers from the market, and how we integrate them between the battery cells in the top part, in the bottom part, and how we evaluate the performance of each of the batteries and each of the material, and the capacity to avoid this thermal runaway catenation. And this is a little bit how we evaluate the thermal runaway phenomena, and how we evaluate the integration of different solutions to improve the safety aspect of the battery system. And if we jump to the next slide, yeah. And here we have the studies that we developed to evaluate the venting gas distribution and after the thermal runaway event. And we develop specific numerical models and validate them throughout testing. We perform several experimental testing process at cell level to track the characteristics and distribution of the venting gases, and these results were used to validate our preliminary battery cell models. And you can see that the validation was quite accurate. And we then apply this data to the BATS design in a higher level. We scale up the venting model, and considering all the specific layout and the design of the BATS solution, BATS battery system solution. This allows us to see how gases spread within the module during venting, and as a result, we were able to evaluate the internal battery pack design and how it works to redirect the gases toward the system and to the vent valves. And this is quite interesting, because with this type of numerical results, you are able to improve first the design of the main structure to be like a conductual design to transfer from the battery cell to the venting valves the distribution gases. And apart from that, you are able to specify the components you will need in the main design to improve the safety aspect, and apart from that, improve the cost of the overall design. And all this information was integrated, of course, after this evaluation in the BATS battery system design. So now we are working in the demonstrator manufacturing to develop the final experimental validation of the project, considering and integrating all these safety strategies. And if we jump to the last slide, and you can see here the main schedule we have. As mentioned, we are going to develop the experimental verification in a demonstrator stage, and this is more or less the schedule we have in mind. As you can see, the demonstrator are currently under manufacturing process, and in May, more or less, we will be able to start with the experimental evaluation, and this will enable us to validate all the strategies we have implemented during the project. And as I must say that everything is progressing according to the plan. That's quite positive. So we are very pleased with the work being carried out in BATS project. And this is more or less what was planned to highlight in this project. Thank you.
Thank you very much, Manix, for intervention. And now it's back to Borja for extended project.
Okay, so we're back again. So before I start, let me quickly remind you what we were trying to do, because all of us are doing different things. So very quickly, just to put into perspective what we're trying to do here. So we're trying to build a finite element framework that allows us to predict the both internal short circuit, internal runway inside a single battery cell. And for that, we have to do experiments that allow us to characterize all our finite element simulations and validate them. So go to the next slide, please. So of course, this is the experimental campaign that we are partners and we did. So this is, let's say, the fun part. Okay, well, we take the cells and essentially destroy them. Okay, and gather all the data. So this is at least from my perspective very interesting and very spectacular. I was not sure that it was allowed to include videos because these videos are quite spectacular. But you all know how PowerPoint works, and sometimes the videos, might not work. So I was not unsure of including the videos. But anyway, so from left to right, you see that we've done a bunch of testing. You're not going to see the results of all the tests, but only few of them because we are limited on time. So, but any of you that are interested, please contact me. I will be pleased to share with you the findings of the project. So from left to right, we have first a crash test. So you see that there's a steel ball that it's crashing onto our battery cell. This is displacement control. Next, we have a nail penetration, which is essentially the same, but instead of a round ball, steel ball, it's essentially a nail that penetrates into the cell. Then we have the overcharge and forced discharge, external short circuit, and over temperature. And of course, over temperature, I couldn't capture anything. So you have a very nice explosion. This is an image from the IR camera that we use to record the tests. So from all these tests, what we're interested in is, okay, we have to make the cell go into internal short, and we have to destroy it essentially to be able to define the criteria that we need in the finite element simulations. And we recorded the voltage, current intensity, temperature histories. Temperature histories, of course, in different points of the cell. So actually, if you see in the third picture, starting from the left, you would see on top of the cell some sort of a glued thermocouples with what it appears to be some sort of a blue tack or something like that. So these are the points where the temperature was measured. And of course, in the two first tests, starting from the left, we have to record the force and displacement to be able to match the mechanical behavior of the cell with the simulations. Okay, so next slide, please. So how do we do these finite element simulations? Okay, so we have to, as I said before, we have to couple a bunch of things. We have to couple the mechanical behavior with the thermal, with the electromagnetic. How do we do this? So the electrochemistry is done through the electromagnetics of the code. For this, the code itself places, in this case, it's a second order Randall circuit at its node. So it solves the potentials between these Randall circuits for every node. These Randall circuits were characterized internally for this particular battery cell inside the project. It was not done in a work package, but it was done internally in the project for several temperatures. Okay. Then the Joule heating is calculated and it's passed on to the thermal solver. And of course, the mechanical behavior of the cell was characterized with the crash test we've seen in the previous slide. So if you look to the bottom left corner of the slide, you will see a force displacement curve of this crash test onto the battery cell itself, where the red line is the solid red line is the finite element simulation. So you see that at least the force displacement curve it's right on top of the experiment. So we were quite pleased, at least mechanically. Then you'll see that you have to do a bunch of things for the thermal and for the electromagnetic. So a few points before I move on. The main contribution to the mechanical response, it's coming from the cell stack. So instead of simulating each of the layers of the cell, what we decided to do is to go from an homogenized approach, which you can do at least in this finite element code. This particular code is LSDyna. You can use any that allows you to do this, but we're used to, we have experience with this particular code, and for us it was much more convenient to do it this way. Of course, we assumed everything isotropic because we don't have any other data that suggests otherwise. At least if you don't do more experiments, you cannot say that the behavior is anisotropic, although I'm sure it is, but as a first approach, it seems quite reasonable. We simulated also the tabs of the cell. They were thermally and electrically and mechanically in contact with the rest of the homogenized cell. And the main challenge, let's say that the experiments allow you to characterize and input all the data you need for the behavior of the cell, but the main challenge here was to define some criteria for the internal short. And you'll see in the next slides how we do it for the different experiments. So if you go to the next slide, I'm going to show you the results of 2 of the experiments you've seen in the first slide only because of the limitation of time. Go to the next slide, please. Okay, so this is an overcharge test. Okay, so what we did here is to input the current intensity we read from the experiment. So you see on the bottom left, you see the current intensity, the evolution of the current intensity over time of the battery cell read from the experiment, and the one that we used, which is right on top, to feed the cell. And then we read the voltage and the temperature on the cell itself. So in red, you have solid red lines, you have the simulation. Okay, so you see that this is quite, so the simulations reproduce quite well the behavior of the cell. And you see that there are certain drops. If you see the voltage curve, the voltage time, you see that there is some drops in the voltage. And if you see on the right, those drop corresponds to quite very abrupt increase of the temperature. So this is when the internal short happens. So at that point, we said, okay, so if the voltage is above a certain limit, in this case is 7 volts, what we're going to do is substitute the Randall circuit that recreates the electrochemistry of the battery cell with an internal resistance that it's very, very small. So that way we create an internal short circuit, but that was not enough to increase the temperature. So we have to add an external source when the voltage drops to 0 to simulate the thermal runaway. Okay, and this is the abrupt increase on temperature that you see on the plot on the right. So you see temperature over time, and you see the red curves are our simulations, and the rest are different. The 3 repetitions that we did for the battery cell. So it's quite, it fits quite well, I think. All in all, seeing the variability, it fits very, very well. So this is one of the criteria that you can come up with. And the last result that I'm going to show you in the next slide, which is another test. Okay, so this is an over temperature test. This is the fun test you've seen in the beginning with the IR camera, where everything it's super, super hot. So in this case, how we simulate this is we added the temperature history that we recorded from the temperature pad that was underneath the cell in the experiment, and we essentially plugged into our simulations the same temperature history. So if you see the plot on the right-hand side, which says temperature and time, you'll see that we have different temperatures for different times. This is because the temperature profiles that were that the cell was subjected to were different. So we simulated only one of the temperature profiles because if one does the job well, the rest are going to be predicted as well as this one. So we went for the fastest one because the simulation, of course, lasts. It's faster, right? So you see that what we did in this case is instead of using the voltage criterion, which doesn't apply here because the voltage doesn't change, only the temperature increases a lot in the cell, we added the temperature criteria. And we set it to 280 C. So when the temperature went above 280 C, then the voltage drops to 0, and we create an internal short circuit in the battery cell. Again, we need an exothermal source, artificial exothermal source at that particular node that replicates the thermal runaway and goes and increases the temperature very, very abruptly, as you see on the plot on the right. So you see that if there's a point at which the temperature increases very, very fast, but then it's almost vertical. And this is symbolized with the white dot, which is around 280 C. And the rest of the tests were, I have no time to show all of them, but they were quite good in terms of reproducibility. So we're quite happy with it. And that's pretty much everything. So if you guys have any questions, I would be glad to answer any.
Thank you very much, Borja. We will do them at the end. So I now the word, and I'm sorry when you asked to switch slide, there is a small delay for the internet connection. Sorry for that. So just be patient for
No
a few
problem.
seconds. just to clarify it. So yes, now it's time again for next bat. And now the floor is yours.
Yep, thank you so much. So in this second session, I will present the results obtained from a series of abuse tests performed of different lithium-ion cells within the framework also in XBAT project. So in the first slide, well, the objective of this work is to analyze how different cell types behave under these representative abuse conditions. So the table shown summarizes the results of abuse tests performed, including 1 thermal test, 2 electrical tests, and 2 mechanical tests. These tests are across pouch cells, prismatic cells, and semi-solid cells. So what we can observe is that certain abuse conditions as crash and short circuit are generally well tolerated. No? But then in contrast, we can see that nail penetration and overcharge clearly stand out as the most severe test. So this highlights the importance of properly defining safety strategies for nominal or abusive operating conditions. So in the next slides, we will focus on the results on one of the series for these 2 most aggressive abusive tests. First of all, we want to focus on nail penetration test. As shown on these images, all tested cells exhibited critical failure. So unfortunately, as Borja says, unfortunately, we are not able to show test videos because they are very representative. But the images shown taken are screenshots taken, sorry, from the original video recording. So in the two images from the left, at initial contact from the nail between pouch cells and prismatic cells, the first reaction was a short swelling phase, but then followed by rapidly venting and also appearance of flames. And then the swelling phase, it observed also at the end of the test. Then in case of semi-solid cell, as you can see, the reaction was faster and more severe. And as shown as in two images, the final leading was the completely disintegration of the cell. So if we continue with the next slide, we could see the comparative response of these different type of cells in case of overcharge under a 1C condition. So also pouch cell and prismatic cell exhibited uncontrolled failure, including venting, rupture, and finally the thermal runaway vent. At prismatic cell, what we could say is, although the venting mechanism enables a more controlled release of gases, the final result, as you can see, the final result observed is that they are absolutely rupture the cell. And then, in contrast, the semi-solid cell showed a different behavior. Although this swelling, as you can see the image, although this swelling was observed, no critical events occurred. So this means that these results indicate a more tolerant response to this condition of overcharge for the semi-solid cell at the pouch or the prismatic cells. Then in the next slide, we will present a further analysis for this severe failure scenario. This additional abuse test is in collaboration with TEA that was performed using a canister. And in this case, the triggering method also was overcharge, but in this case, we choose it. So in this configuration, a prismatic cell was fixed to canister lid, and at some of these serial tests, the cell was also immersed in dielectric oil. During the test, we were monitoring key parameters such as cell temperature, also the voltage of the cell, internal canister pressure, and then additionally, rupture disk, as you can see at the left image, a rupture disk with a pressure limit of 1.6 bar was installed. So the next slide, we will show you that during the test, we were monitoring these key parameters. As you can see at both charts. Also, we monitoring the pressure inside the canister, and voltage cell, and temperature surface cell. So when thermal runaway occurred, the rupture disk opened by the overpressure detected, as you can see in this in this test, the overpressure detected was at some point 1.8, so above this 1.6 limited from the disk rupture. So when the disk is fully opened, then with the thermal runaway course, then we will follow it by this flame release. So also this setup is important because enables an evaluation of thermal runaway under confined conditions, which are particularly relevant for inclusive battery systems. Then for analyze this presentation, we would like to present this slide as a summarize the test results using EUCAR hazard level classification, which this classification provides a standard classification for the severity of battery failure under these abusive conditions. In left table, what we can see is the related EUCAR hazard levels scale in branches. And then in the right table, we can observe that nail penetration, it results the highest hazard level, confirming that it's the most critical of this condition. But also overcharge, as you can see in the table, that leads to hazard levels for pouch and prismatic, and then a little lower from semi-solid. So, and then in conclusion, what we want to present today is that with these results shown, we can confirm that perform this kind of abusive tests are required to provide valuable input for design. Also design safer batteries, and in every design stage. We don't on our part of this development on the design, but we form part of this tests performance, and so we were able to do more of these abusive tests. So thank you again for your attention, and thanks.
Thank you very much, Arnaud, for your presentation. And now we are back for the last presentation from Versaprint and Gael from CA.
Like said earlier, I will focus on this exhaust gas management system. Please, next slide. What we've done on this, we've done typically two types of tests. The first one is just a thermal runaway test to characterize our exhaust gas management system. So we put only one cell under the system, bring it into thermal runaway by overheating, and see how everything react and how our exhaust gas management system behave in real conditions. And then we've done a thermal propagation test. So here we have multiple cells. We trigger one of them with overheating, like always, and then we see what happens to the whole module. And this is what we will see now.
Yes.
Yes. What we've seen is that we've seen some smoke. So the cells are NMC 522, so prismatic 522 cells, 53 ampere hours. So pretty big prismatic cells. If you bring them into thermal runaway in open air, you have a lot of flames, a lot of hot particles, etc., etc. But with our exhaust gas management system, we managed to reduce this event to only hot gases and some thin particles. That's what we've seen in the video. Yeah. No.
Oh, sorry.
That's the video again, please. First second, you have some white smoke. This is electrolyte, and then first it's darker smoke. Those are particles. You've seen some incandescent particle that escaped the filtration, but did not manage to burn the gas outside. So we are pretty happy because our KPI was no flame outside the module, and we achieved it. But we did not manage to block the propagation. We do not see it in the video, but the nearby cells propagate 13 minutes and 21 minutes after. But even with those two supplementary thermal runaway, we did not see flames outside our module. So our exhaust gas management system works even if multiple thermal runaway are done inside the same module. And our plastic casing did not resist those multiple thermal runaway. It melted away after some time. The main result we can see on the next slide is that we greatly reduced the temperature of the gas in comparison between the gas at the exit of the exhaust gas management, between the gas right in front of the venting of the cell. So this is a great achievement. But we did not filter as much particle as we expected. So we roughly gathered 10% of particle, but as we see in the video, the particle gathered are the biggest one, and the one that can escape did not froth the gases into fire. So that's pretty good. And I think that's all for me.
Great, thank you very much, guys. So we are now at the end of this second session. So it is time for Manex, Borka, Arnau, and Miguel to answer the questions. I don't know if we have questions on chat. No, but maybe in the room. Yes.
So I do have some, but I would like if one of you guys in the room will have questions, that would be interesting for the public and for us as well to ask the questions, because this is the last moment we can do this with our project, our partners. I will start with one. Okay, then.
I have a pretty technical question about extended and NextBat. The photos you've shown about your test did not show a compressive stress around the push cell. And we have seen that if we do not compress the cell like they are compressed in the real life, we can have variation into the thermal runaway compartment and behavior. And why did you not compress the cells?
I can answer first. Thanks for the question. It is true. It is true that we considered initially to add the pressure plates, because it was more representative from reality. But of course, if you put the pressure plates, you cannot crush or do a nail penetration test, because the cell is absolutely covered with the pressure plates. You could do probably the rest of the tests, but also if you add the pressure plates, part of the temperature was sucked by the plates themselves. So we decided to, let's say, characterize the raw cell. because at least from our point of view, of course, the rest of the projects might be different. From our point of view, we wanted to be able to simulate the cell without the plates, but that was just us. So we decided to go without the pressure plates. But you're right, the behavior is different.
Okay. Us at TEA, we use a compression plate with holes to do the nail test.
That was, we thought about it. Yes, we thought about making a hole on top of the pressure plates and doing that, but yeah, as I said, we decided not to do it because it was much more inconvenient. But yes, you're right, and that's a good approach actually.
Okay, so do you think the results that you obtain in your TP test, TR test, can be exploited to do a simulation at the module level or a higher level of integration?
I hope so. I hope so. Yes, I hope so. and yeah, I'm willing to at least try it because then it's a little bit more complex. But yeah, I would like to see if we're able to simulate the propagation, the thermal propagation throughout the module. That would be nice.
Okay, thank you.
A couple more minutes for questions.
Okay, so I can start with one question then for the project BATS. You target different applications. In your case, you're the only ones to target off-road and marine. I mean, it's the only applications that you target, and they are quite different from ours, for example. And I was wondering, how could you explain how it impacts, how the application impacts the tests, and especially the safety tests?
Yeah.
For these two applications.
Hi, everyone. I mean, considering the testing process in an overall way, I will say that the application impacts significantly because mainly the requirements of each applications are different. And in our case, as you mentioned, we are talking about marine applications and off-road application, two really different applications that should be fulfilled with no similar, but the same battery system design that is modular. So in this aspect, we evaluate quite heavily all the requirements of the application, and we develop specific use case profiles to develop all the characterization of the battery system. So that's considering the overall testing process, considering the electrical one, the thermal ones. So you have to consider the characteristics of the working environment to evaluate them experimentally. So yeah, the application impacts significantly the testing process. And considering the safety aspects, I mean, if you are talking about nail penetration, only this type of thermal runaway safety aspects, I mean, for marine application, for example, you have to fulfill different standards in comparison to the ones based on off-road. So if your application have integrated special pines or special covers to fulfill this type of phenomena and this type of standards, I mean, in our case, the solution is quite similar, the design. So the test should be applied for both applications. But I was thinking a little bit more in safety aspect, considering the mechanical testing process, because for this, of course, will impact the application because the mechanical behavior of off-road vehicle and a marine application will be quite different, and because of that, we have different profiles to evaluate. So,
Okay.
In a short answer, yeah, will impact.
Okay, thank you. Okay,
4 minutes.
For the last question, I will choose NextBet because we have one person here in the room as well working on this project and one online. So for the presentation, you showed this a system with combining immersion and pressure. Could you let us know with the test results that you have? Is that bringing more hazard? Is that more difficult to control the safety? Is that what you observe, or is it not as dangerous or less or more dangerous than other immersion cooling systems and other non-immersive cooling systems? So you are two people that can answer.
I can say to you some I sense my thoughts. So regarding the immersion and the compression, the combination of both phenomena, it's real challenges in order to know how is the behavior of the thermal runaway of the cells inside the oil and inside a closed volume. It's quite difficult to simulate also. But with the test done by the canister, we can have some values and parameters for one cell inside the canister with pressure, and it's quite a good result because we can have a small difference between the modelization and the results, great results by experiments. Specifically for the peak pressure during the thermal runaway. So that's a good point at this stage, and the next step in
the simulation predicted well.
Yes, yes. And the difference is about 0.3 bars, so it's very close. The next step of this project is to simulate at module level with the thermal propagation site. So on A+ we'll do the module test, TP tests. So let's see it. Yes. Maybe Arnaud, you have more conclusion or opinion?
Yeah, I agree with you that at least we have this test for know how the behavior of the cell to compare inside the canister or outside the canister. So at least we only do the test for recording these K parameters and good comparison the behavior. And then as you said, the next step is to test this for a module level. So we hope we could have more comparison level.
Thank you a lot.
Thanks to all of you. And I think we are perfectly on time. Sorry. Online is good. To conclude the event, sorry. So thanks to all the speakers, to all the participants who attended this hybrid webinar and in-person meeting, I would say. So just to conclude, I would remind you some of the next events from the other clustering projects also. So the next one will be also the 24th of April from Campus Project. It is the final dissemination event. You have the link and a QR code to join the event if you are available. It will be in Brussels, so during the morning. And in October, the exact date is still to be defined, but it will be in San Sebastian in Spain. So it's the final workshop of the project will be hosted by the coordinator of BATS in Civitec. So you're all invited to join this event, and of course for both events, all the information for the registration and also the logistics will be forwarded to all the participants of all the projects, or at least the communication departments so that all the projects can be aware of it. Just to remind you that these presentations and also the recording will be shared with all of you. And thank you very, very much for attending this clustering webinar, and see you next time.
Thank you very much. See you.
Thanks.
Thank you so much. Bye.
Thank you. Bye bye.
Bye. Thank you.